Good afternoon, ladies and gentlemen. Welcome to Physics 30, Atomic Physics, Lesson 3, the Millikan Experiment. Now, Alberta Program of Studies, or POS checklist. Explain Millikan's oil drop experiment and its significance relative to charge quantization. Now, the problem. Thompson, 8 of spades, and if you're new to the class, I have a deck of cards with different physics teachers on them, and Thompson's the 8 of spades. He discovered the electron in 1897 using a gold foil and cathode ray tube apparatus, but he didn't know how much charge was on each single electron. Remember, this was the charge to mass ratio he found? Now, Robert A. Millikan, 8 of diamonds, 1868-1953, designed an experiment to determine the charge on a single electron. The experiment used ideas near and dear to us: charged parallel plates, gravitational electrical forces, and the total force. So, the experimental design is fairly straightforward. Large steel chamber with microscope and atomizer attached. The atomizer sprayed a fine mist of oil into the chamber. Oil becomes charged by friction or by X-rays when passing through the nozzle of the atomizer. Through the microscope, he could watch the oil drops fall. Now, this is what it looks like. So you see here, take a moment to look at it. The atomizer, perfume spray bottle, sprays in oil droplets. Your two charged parallel plates, the X-ray source, and microscope. And no, this did not have the X-ray source pointing directly at the microscope. It was actually up with the atomizer. I had to change the picture. Anyway, so, and note the charged oil droplet between the two charged parallel plates. Now, he placed parallel plates in the chamber and activated it when a good-looking drop came along. By measuring the diameter of the drop and knowing its density, he could determine the drop's mass. By setting the force of gravity equal to the force of electricity, or force of the electric field, electricity, he could find the electric force acting on the drop. By knowing the electric field strength, he could figure out the charge on the drop. Now, Millikan set the force of gravity equal to the electric force. When these forces were balanced, the drops were suspended or achieved a constant velocity, and I want to stress that, or a constant velocity. So force electric is Q electric field, force of gravity is mg. So force electric equals force of gravity. Rearrange, you get Q equals mg divided by E. And that gives us our charge, the one thing we don't know about the electron, or the drop of oil. After repeating the experiment many times for many different drops, Millikan found that the drops always had charges which were multiples of 1.60 times 10 to the minus 19 coulombs. He therefore concluded the elementary charge was 1.6 times 10 to the minus 19 coulombs. And by the way, he's right. If you go to your formula sheet, you see it goes last page, constants, elementary charge, E equals 1.6 times 10 to the minus 19 coulombs. All right. Now, importance of this discovery. Not only was it useful to know the elementary charge value, but this experiment proved that charge is quantized. This means that there is a fundamental building block of charge that cannot be broken down any further: the electron. Now, Millikan did not work alone. He had a partner, a Harvey Fisher, who should have shared in this credit. However, a deal was made between them that Millikan could claim full credit for this experiment if Fisher could claim full credit for another since-forgotten experiment for his dissertation. The oil drop experiment went on to win the Nobel Prize in 1923. Fletcher kept the secret until his death. You feel sorry for him. Like Rutherford's graduate students. Who are they? Don't know. Anyway, there is evidence that Millikan only reported some of the values he got from the experiment. Other values, which would have given his experiment a higher degree of error and less clout, were thrown out. This would have thrown his percent error from about 1% to 2%. So maybe he faked the data, which is never a good idea. Anyway, let's do a few example questions. So, an oil drop weighs 1.9 times 10 to the minus 15 newtons. It's suspended in an electric field of 6.0 times 10 to the 3 newtons per coulomb. Part A. What is the charge on the drop? Okay, first things first, solving a physics problem. Read the question carefully, underline or highlight what you need to know. Draw a picture. Here's the oil drop. Now, here we have to assume, we know force of gravity is acting down. We're assuming force electric is pulling up since it's suspended. That's a reasonable assumption. Okay, now this is EQ, this is mg, so EQ equals mg Q is mg over E. And note, this is mg, the weight, in newtons. 1.9 times 10 to the minus 15 of a newton, divided by the electric field strength, 6.0 times 10 to the 3 newtons per coulomb. Charge there, the math, I got 3.17 times 10 to the minus 19 of a coulomb. Check my math, but I think I'm right. Okay? Now, we can argue, should we round it off to 3.2? Probably. But I'm going to carry it on. So how many excess electrons does the drop carry? Well, 3.17 times 10 to the minus 19 of a coulomb. 1 electron, 1.6 times 10 to the minus 19 of a coulomb. That is 1.98 electrons. Now, I deliberately left it as 3.17. We can argue about it being 2, but it's not 1.98, it's 2 electrons, right? I deliberately jiggled the numbers like that. You cannot have a fraction of an electron. So you have to round up or round down to the nearest whole number. Okay? And notice it's not 2.0 electrons, it's 2. Now, a positively charged drop weighs 6.4 times 10 to the minus 13 newtons. An electric field of 4.0 times 10 to the 6 newtons per coulomb suspends the drop. What's the charge on the drop? And how many drops, how many electrons? Okay, I'm going to pause the recording. You guys do this. We'll come back and compare results. So pause the recording. Welcome back. I got force electric equals force of gravity. Q is 1.6 times 10 to the minus 19 of a coulomb. All right? Now, how many electrons is the drop missing? 1. I'm not doing that. You can convert 1.6 times 10 to the minus 19 times 1 divided by 1.6 times 10 to the minus 19 and get 1. Now, better question. If 3 more electrons were removed from the drop, what electric field would be needed to balance the drop? Well, once again, oh, sorry, wrong. Poor choice of colors. It's a much better question here. Force electric, force gravity, capital E, Q. It's physics, Mr. Sutton, don't get that excited. All right, now, if 3 more electrons were removed from the drop, now, how many were removed already? 1, so we're missing 4 electrons. Okay? So, here, EQ equals mg. Look for the electric field. Now, what is the mass? I don't know, but I know the weight. What? 6.4 times 10 to the minus 13. 0.4 times 10 to the minus 13 newtons. Now, what's the charge? 4 times 1.6 times 10 to the minus 19 of a coulomb. So, do the math there. What electric field strength E do you need here? Well, I got 1.0 times 10 to the 6 newtons per coulomb. Okay? Now, that's what I got. Questions? It's a pretty straightforward concept once you get it. Now, I'd like you to work on the oil drop questions for homework. And if you have any questions, shoot me email. Otherwise, I'll see you in class tomorrow when we can work on the lab for this. Have a good day.